So hello, thank you to all the previous presenters. I'm going to present some work that we recently concluded about the impact of cool roofs on the efficiency of photovoltaics installed on urban roofs. I have tried, it's quite a technical subject, so I have tried to keep it as brief and painless as possible. So I would also like to pay my respects and acknowledge the Betugal people who are the traditional custodians of the land which this meeting takes place, and to elders past and present. And as almost all of you previously mentioned, renewable energy sources have penetrated the energy market during the last few decades, and they currently represent approximately 30% of the global electricity generation. Of course, hydropower represents approximately 55% of the total renewable energy production, with around 25% coming from the wind and another 10 to 15% coming from, let's say, photovoltaics. Currently, solar panels are mainly installed in rural areas, in open areas, but we also have building integrated photovoltaic panels, which of course can be installed on building facades and on roofs. Of course, roofs are more popular because their photovoltaic panels are less shaded, and currently the building integrated photovoltaics represent approximately 40% of the annual PV installations. However, the crystalline photovoltaic panels that we usually use on roof installations present an albedo which is lower than 10%. And the surface temperature can, under clear sky conditions, of course, be 70 or even 80%. And you can see on the graph on the left, which is a study conducted by the high performance architecture, by members of the high performance architecture group, that the temperature, the surface temperature of photovoltaics on roofs in Greater Sydney is approximately, the average is approximately 30 degrees, but it can reach in hot and clear days, it can reach temperatures of 90 degrees. And there are several adverse effects that are associated with the use of the photovoltaics in the urban context and potentially affecting the thermal balance of our cities. So high surface temperature of the photovoltaics, of course, translates into higher sensible heat released into the urban atmosphere and contributing to local overheating. And there have been some comparative measurements of the sensible heat released by photovoltaics against other urban surfaces that show that the sensible heat flux released by the photovoltaics can occasionally be even 80% higher than the unshaded ground in the cities. This is another study that has been performed by some of the high performance architecture group members. There have been several experimental and mesoscale climatic simulation studies based on accurate thermal assumptions. And they have concluded that the use of photovoltaics in the urban environment can and may increase the average ambient temperature in the cities up to 1.5 degrees Celsius, while the surface temperature can be increased up to 2.5 degrees Celsius. And this is a different study again. The increase, of course, of the ambient temperature is not only causing discomfort in our exterior areas, in our urban areas, but it can also have a significant urban microclimate, but also an energy penalty. This study evaluated the impact of photovoltaic solar panels on urban temperature and corresponding cooling load penalties in 17 representative building types for 2 summer months here in Australia, for January and February in the area of Sydney, in the Greater Sydney area. And the study showed that when 25 to 100% of area of the roofs are covered by solar panels, the ambient temperature may increase from 0.6 up to 2.3 degrees Celsius. And this temperature increase can, of course, lead to the cooling degree hour base of 25 degrees to be increased by 10 to 32%, and 6.2 to 19% in the coolest and hottest weather stations in Sydney, respectively. And this, of course, corresponds to 1.7 and 6.8 kilowatt hours per square meter increase in the cooling load during these 2 summer months for these representative building types. So we have this, let's say, adverse phenomena that are caused by the overheating of the solar panels. But then we also need to look into the efficiency of the solar panels. And we know that solar panels efficiency depends on many parameters, especially on their orientation, the tilt, the elevation, the location, of course, where they are installed. But their efficiency is a strong function of their module temperature. So under nominal conditions, for every 1 degree Celsius increase of a crystalline silicon cell module temperature, there is an efficiency drop of 0.45%. While for the thin film modules, the efficiency could be 50% lower in the urban context. And this is what the lower graph can show us in the left. So what are the parameters that can increase the temperature of the solar panels in our cities? Of course, we know that the urban heat phenomenon is increasing ambient temperature, is increasing the temperature of the air, and this increases the temperature of the modules, but in turn, the large implementation of PV modules on the roofs, especially in urban environments, may accentuate local overheating, which in turn may deteriorate even further the performance of the photovoltaics, and this creates this very bad cycle. Second, the dark color of our roof surfaces, which typically absorb the solar radiation, results in significant increase in the air temperature above the roof and around the modules. Of course, a comparative assessment of the performance of the freestanding and roof-integrated monofacial photovoltaics has shown that there is an average annual temperature difference of 3.2 degrees Celsius and a 3.5% reduction in the energy production of the roof modules. So considering these conditions and considering the urban heat island and the increased temperatures in the urban context, but also the dark roofs and the solar panels and the heat added by the solar panels, it would be useful to investigate if and how cool roofs and cool roof materials, apart from improving the microclimate and reducing the cooling load of the buildings, can also improve the efficiency of the photovoltaics that are installed on urban building roofs. We know that cool roof materials can present 40 degrees lower surface temperature compared to dark roof materials. But we also know that in warm climates, the sensible heat released by the cool materials can be up to 72% lower than the dark roofs. So we can assume that these materials can reduce substantially the ambient temperature around the panels, probably decrease the front surface temperature, increase the reflected radiation towards the back of the panels and increase their efficiency. So what we did is we tried to review some of the available studies and see how much can the reflective roofs improve the efficiency of monofacial and bifacial photovoltaics on the roof of urban buildings, and also see which is the optimum combination between the main installation characteristics and the albedo of the roofs for specific locations. So what we did is that we analyzed 15 studies, reporting results of 70 case studies carried out in 16 cities. 11 of the papers were on bifacial photovoltaics, covering 57 different case studies in 14 cities, and the other 4 papers were on monofacial photovoltaics in 13 case studies in 5 cities. And this is what we found about the relationship between the increase of the roof albedo and the increase of the annual energy production of monofacial photovoltaics. Here we had 13 case studies assessing the impact of the albedo, 11 of which are based on simulations, while only 2 were experimental studies. So the impact of the roof albedo on the annual energy production of the monofacial modules depends mainly on the geographic location and of course the tilt and the azimuth of the panels, and the association of the albedo increase and decrease of the energy production is found to be almost linear. This means that an increase of 0.1 in the albedo corresponds to a rise in annual energy production of around 0.7%. Of course, more case studies, especially experimental case studies, would give more concrete results. We also studied other parameters, especially the association of the tilt in the albedo, and found that for higher albedos, the tilt should be increased to a certain degree, up to a certain degree, and also for a given roof albedo, the annual energy production of monofacial photovoltaic modules seems to be insensitive to the elevation of the modules above the roof surface. And this is the respective results for the bifacial photovoltaics, and this graph presents the association, of course, of the increase in albedo and the annual production. And we considered here 57 case studies. Most of them were simulations, 51 were simulations, and only 6 were experimental studies. So the graph shows that for an increase in the albedo of 0.1, the rise in annual energy yield for the bifacial photovoltaics can be around 4.5%. And of course, these results are representative for this group of studies, or for case studies. However, the used data cover a wide range of climatic zones, as well as a wide range of installation characteristics, and can be considered quite representative. The results provided by these case studies present a significant consistency under similar installation characteristics and conditions, and they are expected that future data might probably be described by this relationship. However, we need to note that there is a very considerable difference between the coefficients of the experimental data and the simulated data. The coefficient for the experimental data is around 26, while the simulated, the same for the simulated is 45. So there is this distance, and there is a big need for more experimental data on this in this area. So we also studied the optimum relationship between the albedo and the panel elevation and the location latitude. And generally, we saw that for higher elevations, the increase in annual energy yield of bifacial modules is higher for specific albedo values. So just to sum up Lana mentioned all the different technologies and measures for the urban heat island and to cool our cities, but there is a need to install photovoltaics in our urban roofs, and I think this is going to be more and more popular and common, especially in Australia. But we see that cool roofs and the new materials for cool roofs have very good results in not only cooling the environment and reducing the energy consumption for cooling of the buildings, but also increase the efficiency of photovoltaics on roofs. And this is one direction for new studies that can be conducted so that we have more and better results on the association of these parameters. Thank you very much.